what if I told you that you can get your skills on topology on another level? Everybody knows that on a metric space, you can characterize functions, understand properties of the space with sequences, which are neat things, neat structures, mathematical structures that are just very useful. But what happens when you have spaces that are more general than that? Well, in fact, it doesn't even need to be a metric space, because sequences work fairly well on something called first countable spaces. And every metric space is a first countable space. So this is a type of space that is more general than metric space. The definition is the following. For each point, there exists a countable neighborhood basis. So suppose that you have a point in your space, then there must be some, let's say, some family. It must be countable. I'm putting like this, that is countable infinite, but it can be countable finite. So it just as well like that. And so there exists this countable neighborhood basis. I mean, every one of these is a neighborhood of X, and the property is the following. If you have a neighborhood, another neighborhood of X, let's say V sub X, this is a neighborhood of X, then there must exist some index in the naturals such that X is inside this, let's say, n hat, and this is inside this neighborhood. So that's the property that is called being first countable space. So in this kind of space, limit points, continuous function, and compact sets can be characterized by sequences. But in general spaces, it doesn't need to work like that. So sequences fail when you have spaces that are not a first countable. Well, the good news is that there's another mathematical structure which is more general than a sequence that can characterize all of those things in every topological space. So it doesn't even need to be first countable, it can be just any space. And that thing is called nets. So nets are structures that are, well, it's not a structure, nets are functions that are defined on a domain that is called a directed set. So here we have an example of a net that has a nice property that every vertex has an immediate successor, so we can just depict it like a kind of graph. But in general, it doesn't even need to be like that. You can have a net inside uncountable sets, like for instance the open interval on 0, 1. It can be represented with a net. So the first definition is the following. Recall that a partial order is defined like a relation and a set that satisfies these three properties. The first is usually called the reflexivity. This is reflexive. This is usually called anti-symmetry. And the last one is, of course, transitivity. So examples of partial order are, for instance, your usual relation of order in the real numbers. So this means that this is positive. And that means that it is inside some special set that we can call R plus, and the usual concepts of fundamentals of mathematics. All right, so but partial orders are more general than that. The partial order of the real line is in fact a linear order. which is stronger than a partial order. But partial orders can be very general. You can get, for instance, there's a partial order about who is in a higher position than other elements. So if we have these dots here, and we will say this is in a lower position than this, so this is less than that, and this is lower than that, so we can write that, and yeah, just like that. And you can see fairly easy why this is transitive, and this is also transitive. And well, just to make sure you can define that every element is in a lower or in an equal position than itself, so it's reflexive. And the anti-symmetry is also clear. So yeah, that's a toy example on partial orders, but we can get very general with that. So the next definition is something called a directed set. A directed set is a partially ordered set such that for every pair of elements there is a third element that is bigger than those two. So that element could be one of them, in fact, but could be another. For instance, I can give you a quick graph. So if we have the same example of the real line than before, so let's say this is 0 and this is 1. Well, for 0 and 1, we can have a number like 2 that is bigger than 0 and it is bigger than 1. In fact, it's not necessarily unique, because besides 2, 3 also holds this property, and in fact, the same number 1 holds that property. So this new element doesn't need to be different from any of them, and it's not necessarily unique also. For our previous example of the relation of highness, let's say we have 2 points here and there's a third here. So it is directed in that sense because, you know, every pair has something that is above or equal to them. So in that sense, those examples of things that are not directed sets. If you have a partial order set with 2 different maximal elements, let's say something like that, this is not a directed set. So not examples. Not examples are partially ordered sets that we can write like posets that have 2 different maximals. So maximals are like local maximums. So these 2 elements are maximals, and the existence of these 2 elements without a third that is bigger than any of them makes this set not a directed set. So this is a not example. Alright, so the next concept is called being cofinal in a set. So we have a subset of our partially ordered set, and this set is called cofinal in A if we have this property. So every element of A, for every element of A, there must exist an element inside this set that we say that is cofinal, such that it is bigger than that set. So examples of things that are cofinal. For instance, if we were to have, once again, the real line, well, it happens that the set 0 towards infinity is cofinal in R. Well, simply because for every element, let's say -1, there's an element here like 1, 2, or 3, such that -1 is less or equal than any of them, let's say 2. It is also clear that if your set if your poset has a maximum element, if let's say if A has a maximum, let's say M0, this is the maximum, or let's go with capital letter M, then K is cofinal if and only if M0 is inside of K. That should be clear, right? So if you have something that is on the tip of your graph, then you gotta have that element inside of your set for it to be cofinal. But on sets that are not, doesn't have a maximum, like the example of the real line, you can just have some subset like that and it will work. It doesn't even need to be like this. It could be, for instance, the set of natural numbers. The natural numbers are cofinal in R. So lots of interesting examples that we can imagine with these definitions. So the next is a proposition that tells you that if a directed set, let's call it A, and you have a set that is cofinal in A, then K is also a directed set. Nice property. So let's do a quick graph of this. Let's suppose that we are working with a directed set that has a maximum. This is our element M0. So let's just draw something like that. And we have a set that is cofinal in A. And we know that we must have that maximal element in our set for it to be cofinal. And just for the sake of it, let's put another element like this. Let's call this A, and this is our M0. So let's suppose that K is that set. This is, of course, a directed set. Alright, so is K directed? Is it directed? Well, let's review our definition of directed. Let's say we have any two elements. Well, we only have two, so for A and M0, is there a set, an element in K that is bigger or equal than both of them? Well, it's of course M0. And if the pair is A and A, because we never said that the two elements had to be different. If the pair is A and A, well, the bigger element is A, or it could be M0 too. So yeah, this example works. Now, it should be quite trivial to see why this works. Well, if A, let's say, K is cofinal in A, so why do this works? Well, let's say we have two elements, A and V, inside our cofinal set. So that means that they are inside of A. And since they are inside of A, then there must exist some element in K such that, but that already tells you that K is directed. So it was quite easy to see. So moving on, we have another definition. Just like with sequences, we can talk about convergence of nets. So a net is said to converge to a point of the space if for each neighborhood of X there exists some element in our directed set such that every element that is bigger than this has that property. So this is fairly similar to the definition of convergence of sequences in topological space. It's in fact the same. Just the difference is that for sequences, A is the natural numbers. The natural numbers are easy to see that they are a directed set. Now we have a theorem that we will not show the proof, but it says that if X is a Hausdorff space, then any net in X converges to at most to a point of X. So this is exactly what happens with sequences. Sequences in Hausdorff spaces converge to at most at one point. It may not converge, but when it does, it's to a single point. So the same happens with nets. Now, one of our main theorems is that a characterization of the closure of a set. Let's see that. So if you have a set, an arbitrary set, the closure of this set is characterized by this property, by the existence of a net in A, not in X, in A, such that it converges to X. The next is an equally important theorem that is about continuity of functions. So if you have a function from one topological space, whatever that may be, to another one, then this function is continuous if and only if for every element in the domain and every converging net in the domain that converges to X, the net, this one, in the codomain converges to the image of X. So this theorem tells us that in fact this is a net for stars, because it is quite easy to see why this is a net, because you know a net is just a function from a directed set. So if you keep that directed set A, you associate that with X, and this is, let's say, n of A is inside of X, then you compose this function with another function and you will have this, and this composition is also a net. Alright, so you have a net, and it happens that the function f is continuous if and only if this net inside of the codomain converges to the image of the convergence of the net in the domain. So it is once again the same property that you had on first countable spaces with sequences. This is the sequential definition of continuity, but now you have it for any kind of space. Now we also had something called a subsequence when you were working with sequences, and it was defined quite simply. For instance, you have the indexes 1, 2, 3, and 4. You then get a subsequence, taking for instance the odd numbers, and that worked fairly well. You define that subsequence with a non-decreasing function and stuff like that. So for nets is quite the same. Let's say we have a net, which is a function from a directed set, and V is another directed set. We have a function G, let me highlight that, from our new directed set, and this function preserves order in that sense. So the function keeps the order in check like that. And this function has the property that its image is cofinal in A. Coming back to our previous example of sequences, it was stated that this function had to continue towards infinity, right? So it was necessary because you couldn't have subsequences that ended in 5. No, the sequence needs to go on just the same, but in this case the concept that we use is the cofinality. So the image of this function g needs to be cofinal in A. Right. Then the function that is the composition is called a subnet of F. And I want to highlight this fact because with subsequences we had, you know, our set V was a subset of A. For instance, these are the odd numbers. It's a subset of every natural number. In this case, it doesn't need to be a subset, not necessarily. Now the following proposition is very important. If you have a net in X that converges to X, then any subnet also converges to X. And this follows fairly simply because the definition of convergence, you know, suppose that you have some neighborhood of X, then because of convergence there must exist some let's say M inside of our directed set, such that if this holds, then XA is inside of U, right? This is the definition, the usual definition. But what happens if we have a subnet? This element M may not be the image of some J of, let's say, R. It's not necessarily, but surely one of these images should be bigger than M. And why is that? Well, because the image is cofinal in A. Then the cofinal set should have an element that is bigger than M. So this works. And then every element that is bigger than that inside of the cofinal set, let's say G of S, should hold that property that is bigger than M. Then using this condition, because this is an element of A, we will have that X of G of S is inside of U. And that is a definition of convergence. So that's the proof, very simple. Now the following is a definition. It says that a point is called an accumulation point of the net if and only if for each neighborhood of X, let's say U of X is a neighborhood of X, then the set of all the indices such that X of A is inside of this neighborhood, this set is cofinal in A. So this is cofinal inside of A. And so if that happens, then it is said to be an accumulation point. So this one now is slightly different than the usual definition of accumulation points that you can have with sequences. An accumulation point in general is, let's say X is an accumulation point of some subset A, if and only if every neighborhood of X contains an element that is different from X inside of A. So this is different from the empty set. But then we take the set of indexes like that. So let's say that we represent our net with a function, right? That is from A, the directed set, towards the topological space. So this is in fact the pre-image of U of X. It is that. And this is cofinal in A. So that means that for every A inside of A, that there must exist some B inside this set, let's call it K, such that A is smaller than B, smaller or equal than B. So how is that equivalent to our usual definition of accumulation points? Well, Well, for starters, it tells us that this set is non-empty, because you cannot have existence at all if the set were to be empty. So it needs to be non-empty. Then the next thing that tells us is that for every element in the directed space, there's something here that is bigger than that. So what happens if X were to be inside of this? I mean, what happens if X were to be equal to some f of R? Well, if that happens, then we are not interested in X, because I mean, if we want to make this connected to our usual definition, this is let's say this is the standard definition. So well, because this is an element, R is an element of A and K is cofinal in A, then there should be some S that is bigger, S in K. So if S is in K, then given this definition, we will have that f of S that we can write like this is inside of this. Now I need to tell you that from here we cannot quite get here, because X, this element, may be equal to X. Let's see that in detail. What happens if you have a constant net? Let's say that every x of A is equal to some x hat. Then suppose you have a neighborhood of X, U of X. Then the pre-image of this set will of course be the whole directed set, because as we were saying, this net is constant, so everything maps towards this element here. And given that this is a neighborhood of X, of hat X, X is inside of this set, then all of the elements of the directed set should be there. So if this is a directed set, then it is automatically cofinal in A, just by reflexivity. Then it follows that this should be an accumulation point of the net. But it is not, it's not an accumulation point of, let's say, the image of the net. It is not, because it is in fact an isolated set for most topologies. So there is a difference between accumulation points of topology in general and accumulation points of net. So keep that in mind. But that doesn't stop us from stating the following theorem. If X is an accumulation point of a net, well, it happens that this only occurs if and only if some subnet, this is existence, subnet of it converges to X. So this is a result that we quite had in sequences that goes fairly well with nets in general. And finally, the theorem that you were waiting for. A set is compact if and only if every net in X has a convergent subnet. So this is the final characterization of topological spaces that we wanted. When you have a first countable space, instead of nets, you could have sequences, and instead of subnets, you could have subsequences. But in general, for every topological space, you can have these characterizations by nets. So this is it for today. If you enjoyed the video, please consider subscribing and leaving a thumbs up in the video. And if you have any questions regarding the proof that I didn't quite work, you can leave in the comments and I can give you some hints about that. So see you around on our next video.